we will, if we have time, and otherwise we do it tomorrow, talk a little bit about how does this connect to a notion that has been called typicality, and which to some extent can serve as a foundation for statistical physics in general, because it is not based on any particular assumption, but something that is called the concentration of measure phenomenon, which is much more general than so basically what we will see is that the asymptotic equipartition property follows also from typicality assumptions quite straightforwardly. So the first thing to notice about entropy is that it's probably one word for various meanings. So it's has not a really unique definition. So there are several proposals on how one would define entropy. Boltzmann was probably one of the first and probably the most easy one. So if you have a number, if you have choice, then in physical systems, these numbers are usually very large. So the number of states would be something 10 to the power 27 or so. That's very quickly achieved. And Boltzmann actually originally worked with these numbers. So he really worked with multiplicities directly. But in order to have more smaller numbers, he later took the log and said, okay, entropy is the log of the multiplicity, which in many ways is practical because the measure now becomes additive and not multiplicative. And but otherwise, there's little reason. And the second thing is that it worked very well for explaining or for capturing the properties of the thermodynamic entropy. So Clausius entropy, as it was introduced by Clausius and the Canots and so forth. So we have one realm of entropy definitions which come from Boltzmann and later Gibbs. And then we have the original one coming from thermodynamics. And then we have a third one, which comes from information theory. So starting basically with Shannon. And probably there are more, but that's the three I would like to mention today. And the point is that as long as we are always looking at equilibrium systems or IID systems and IID, so independent, identically distributed processes are usually a model for equilibrium systems. Why? Because we assume that the probability to sample some particular state from the systems would be time translation invariant. So every time you sample from the same distribution, which basically means sampling from an IID process. And as long as we stick to that, we always end up with the same functional. We end up with the Shannon-Gibbs functional, and as we will see, this functional does only hold in this case, but there is a generic way to actually derive the right functionals for, I would now like to say, for any process class you are particular to, but of course in many cases this will be very difficult, and there are only a few cases where you can do it in closed form, and one of these cases we will also talk about today. So let's first ask the question, what is more general? Is it Boltzmann entropy, which is simply says, okay, take the multiplicity with which some event can happen, then divide by the numbers, by the degrees of freedom, so that you get the reduced. So this would be simply what is called the entropy, and then with a constant of information here, or in that case it's the Boltzmann constant, and then if you want what physicists call the reduced entropy, you take the entropy per degree of freedom, so you divide by the degree of freedom. And then on the other hand, we have the Shannon-Gibbs entropy, which already contains a distribution function where we do not have a distribution, seemingly do not have a distribution function here. And so actually, over the most part of my active career, and even I believed so in the beginning, we always thought Shannon-Gibbs entropy is more general than Boltzmann entropy because it accommodates some information about the distribution of states. However, this is a little bit of an illusion, and how to resolve this is in the following way. So if we have IID processes, what does this mean? We sample, let's say we have a sample space with W different elements. This could be, if these are spins, this could be 2 to the power n different ways how to orient n spins. So this could be a large number. And now if you ask how likely is it to observe a particular histogram? So if you have W different states and you take n measurements, you will find your system Ki times in a particular state, and the sum over these Ki's, so the sum over the histogram will be the number of observations that you made. And if you ask now, how are such histograms distributed? If your underlying process is IID, then you get basically the multinomial distribution function. And the multinomial distribution function reads multinomial coefficients, so n factorial divided by product over the Ki factorials, which simply means in how many ways can I orient, can I make distinguishable configurations of my states. And then we have as a multinomial coefficient times the sequence probability. So we have how many sequences we have with a particular histogram, and then we have the probability of a particular sequence having a particular histogram. And what is of course nice with the IID process, it's the simplest so-called exchangeable process. So you can reorder your observations and the probability will remain the same. So if we now use Boltzmann prescription, and multiplicity in the IID case is now the multinomial factor. So I have one observation, that's the histogram. We have one reference sequence, which may be any sequence that has histogram K. And now we know such sequences with this probability happen n over K times. And now we simply use Stirling's formula, we apply Stirling's formula, and we see that 1 over n, so n is here now the number of degrees of freedom, so we look at the reduced entropy, and so 1 divided by n logarithm of the multinomial factor, and a little bit of algebra. So we just need the leading term of the Stirling formula, so we can express n factorial basically by n divided by e to the power n. Then we would have a factor 2pn, and some, if we want higher orders, we can add them. But actually, we don't need them. So this would only give finite size corrections to the entropy formula. And we see that asymptotically with n to infinity, we get back Shannon entropy. And this is not new. This was already done by E.T. James many years ago. And also what should be noted is that the pi in the entropy formula is actually not the probability to observe I, it's the relative frequency of observation. So it's really the empirical distribution that you measure. It's not the underlying abstract probability with which some the states are sampled. So this is done with a different functional. So we now take the second part of the multinomial distribution function, namely the part that describes the probability of observing a particular sequence with a particular histogram. So if the probability, so now the Qi is now the abstract probability of sampling I, then sampling a sequence with histogram K would simply be the product over I, Qi to the power Ki. This would be the log of the sequence probability scaled by the numbers of degrees of freedom. And if we now do that, then we basically get sum over pi, so minus sum over pi log Qi, and this is what is called the cross entropy. And so what we have now is that we can actually reproduce from using simply the Boltzmann prescription the standard formula of information theory that the Kullback-Leibler divergence is the cross entropy minus the entropy. And that is a generic formula which we will demonstrate in a second, actually holds very generally for a huge class of processes, only that the information divergence will no longer be the Kullback-Leibler divergence. The entropy will no longer be the Shannon entropy functional, and the cross entropy will no longer be the Shannon type of cross entropy. And the point is that we will not change the entropy prescription. We will stick with Boltzmann entropy. The only thing is, if you apply Boltzmann's prescription of what entropy is to different types of processes, you may find processes where the same thing is possible, and this is actually also something quite generic, at least in the large n limit. And we will also see why. That the reason is measure concentration of measure phenomenon. Asymptotically, you usually can factorize the probability of observing a particular histogram into a multiplicity and the sequence probability, and this sequence probability is widely independent of the order of the observations, at least asymptotically. This remains true, so that we use Boltzmann entropy, but because the underlying process now has a different multiplicity, we end up with a different functional. We do not end up with Shannon entropy anymore. Okay, so that was now the classical IID case and how this connects Boltzmann entropy with the classical formula Kullbaum-Kleiner divergence is cross entropy minus entropy. And in fact, if one now would say, I think I didn't add a slide. No, I didn't. But that's something we can maybe discuss in the afternoon and do it on the blackboard. By the way, if you want to stop me and discuss or ask something, just do it. Just interrupt me. We have time. So sorry. The cross entropy. If you now were to say, okay, Q, we take Q, the prior so the sampling probability to be of the form. Actually, that's something we could immediately do to be of the form. To be of has the form of the Boltzmann factor. If one does that, and we say, okay, we have here the cross entropy S cross is minus sum over Pi Qi, and Qi is the Boltzmann factor, then we can actually see very quickly that we have here minus sum over instead Pi up, and then we have here log Qi, so we get away with the minus, and we get here, okay, that's done, and here we have log Z plus Pi. So this is then oh, that's not gone. So we have here this is log Z plus U. So one actually sees that by inserting the Boltzmann factor for Q, the cross entropy attains a form that then looks like the constraint terms that we add in the usual maximum entropy principle, where we would say, okay, we maximize general entropy, in that case, minus alpha sum over Pi, that would be the normalization constraint, and minus beta sum over Pi epsilon I minus U. Oops, this would be the energy constraint, and alpha and beta would be so-called Lagrangian multipliers with which one can add constraints to a extremal principle, and that here. So this one we always have to add by hand, basically, because we know that PIs are normalized, and this one actually is identical to what the cross entropy does here. So the cross entropy implements basically the constraints on the system. That's how one could think about it. Okay, now with what I've said before, and that is something actually we did with the now unfortunately late Mary Gell-Mann, so he was very interested in that, is that asymptotically we can perform the same program for different processes. And one process in particular we will look at later. So we can look at the probability to observe a particular histogram of a process after n observations. There's a misprint that Q should also be a theta. Theta meaning simply now in the IID case, Q to Qi parameterize your process space. They are the probabilities, the sampling probabilities. in general, for general processes, this could be some other set of numbers. So given that that should be a theta, this probability of observing the histogram can now be factorized again into a multiplicity factor and a sequence probability. And then we can do the same thing. We can identify the information divergence with the log of the histogram probability, the entropy with the log of the multiplicity, and the cross entropy with the log of the sequence probability. And then the formula that we had before from the iid case, divergence is cross entropy minus entropy, goes on and extends naturally to a much wider class of processes. Yeah, okay, there are two ways to see that, or there's a old, very well-known way that has been actually reinvented several times. This is the so-called exchangeable processes, and with this we would go to what is called the Definitis representation theorem of exchangeable processes, which basically is a mixture process of iid processes. However, I would like to point out that there exist exchangeable processes that are not iid. For instance, the Poyer-Earn process is not is actually a path-dependent process. It's not an iid process. A very interesting process because it's clearly a process where the time average does not is not equivalent to the ensemble average. It's a system with self-reinforcement. So it's Poyer-Earn is you have an urn with a number of balls of different colors, and you pick a ball, and let's say it's you have yellow, green, red in your urn, and if you pick now a yellow ball, you do not just replace it, which would be selection with replacement, which would lead to iid processes, but you actually reinforce it. If you pick yellow, you put the yellow ball back, and you put some additional yellow balls into the urn, which reinforces the probability of observing yellow in the next draw. And it's a quite, I will not go into details, but it's a very interesting, it's exactly for the reason because that ensemble averages and time averages do not agree anymore. This is a very nice playground for exploring this discrepancy. We are most of the times actually looking at the time averages here. We are not looking at most of the time, not ensemble averages. The second way, so for exchangeable processes, this is true all the time. It's also true that mk in that case is always the multinomial factor. The only thing that is now different is that the sequence probability can be quite different from the iid case. And so which basically says we are maximizing again Shannon entropy, but under a different set of constraints. The second way how we can arrive at such things, even though the processes are not exchangeable, is asymptotically, and that's maybe we discuss it still today if we have enough time, otherwise tomorrow, using what is called typicality, where one can show that if you have a measure of concentration phenomenon in your process, that actually all paths, now I have to be careful now, they are not really all having, so what you're doing then is you're defining a set of a subset of states that basically takes all the probability, so the asymptotically you will have chance one, almost certainly you will pick a path from the typical set, and even though they are not really all having the same probability, one can squeeze the probability of these sequences in such a way that the error that one makes by assuming that they're all having the same probability also goes to zero, at least for all quantities that we are interested in. Okay, so now that we have somehow discussed the general situation from the classical perspective of iid processes, let's look at one example. And the example is actually, you can think of it as a very simple example of a non-equilibrium process. You can even take it literally as say, okay, it's the staircase process, and the ball could simply be a tennis ball. I mean, so you have a reservoir now of tennis balls up on the top of a staircase, and now you start throwing these balls into the staircase, and what you assume, we idealize the situation, is that the ball can only bounce downwards, and in reality we will sometimes see balls hopping up again. But so we assume now that whenever a ball reaches a particular stair, that the next stair you choose is only below it, except once you reach so that's the slow driven case. Once you reach the ground state, oops. Once you reach the ground state, you can reset the ball to any stair you want to. One can also make the stairs of different width, so we can assign them a probability or a weight, so that if you now set the ball to any state, you would do that with this distribution function. And also, if the ball jumps downward, you would renormalize this stair width in such a way that the ball selects one of the stairs below with this particular weight. So we are mixing two processes. The one is what we call sample space reducing, because every time you make a move, your sample space actually shrinks, and until the last you reach the ground state, and you have to expand again, because if you don't, you get stuck in the ground state. So what you could see here now is something like a very simple dissipative system where you have a stochastic driver cycle. So the system relaxes, and then you have a driver event resets the system. So that would be the primitive interpretation. And the one with the same right, one could simply say this is a model of dissipative systems, because you could now assume each of these stairs is actually a microcanonical ensemble at a particular energy level. And the only thing is now that your system occasionally can dissipate energy into an energy sink and jump downwards. And at some point, you couple the system to an energy source, and the system can go up some levels. So if one does that.
Sorry, what do you think this kind of load vector is
Sorry?
charged?
Ah, thank you. I thought I had it plugged in. It's better than having a black screen all of a sudden. So with this process, I can now easily convince you about how does the multiplicity factor look like. And one actually can derive the multiplicity factor quite easily by making a table. And in fact, we now say a run is now each path segment ending up in the ground state. So we always look at the path the subsequence where the ball ends up in the ground state. Here we would, for instance, sample W-1 and then jumps to whatnot, and then to 2 and to 1. In the second line, we would start here, then go here, and so forth. So you would make a loop where you simply have here your states. Here you repeat your SSR moves and you record them. And now you can see the following, that you can now say read off the histogram. You just count the number of asterisks here and get to your histogram. What should be noted is that the K1, because we know that the system always ends up in the ground state, K1 equals to the number of times we repeat this. And with this histogram, we can now easily ask ourselves, how many different realizations can we find of balls running down the staircase such that we end up with the same histogram? And this simply is in each column, we can now actually reshuffle the asterisks in all possible ways. Yeah,
I'm a little confused about how to read this table. So you start in any one of the W states,
yeah,
and then you let it run, so to say.
Yeah.
Starting in any one state, that's the asterisk in this table.
Yeah. So then the line says, okay, I jumped over it, and the asterisk simply means the next state.
Okay.
That is something.
Right. So let's say you unfold the first row with the 1. You start in W-1. You jump over W-2, and then you get a bunch of other asterisks until you end up in 2. That's how you should read it.
Exactly.
Okay.
Yeah.
Okay. Good.
So then you sum up the column, you get some number.
Yeah.
And then you ask yourself, in how many different ways would I get the same histogram? And then you see, okay, I have here, for instance, KW asterisks in that column, and so I have the column has K1, so R different entries, so I can redistribute my asterisks in this column in K1 over Ki, or K1 over KW in this particular one, different ways. And also I can redistribute that one in K1 over KW different ways, this in K1 over KW minus 1 different ways, and so forth. So the multiplicity factor for the staircase or for the SSR process is now not the multinomial coefficient anymore. It's the product over these binomial coefficients. So we get a different multiplicity. By the way, this process is still a Markov process, so that we are still in a range, in a realm of well-behaved processes where a sample average and time average coincide, so that we don't get the problem that we get, for instance, with the polyiron, that those two do not match anymore. So in that way, we are still in a relatively well-behaved domain. And now we can derive an entropy. And that would basically be an exercise that might be a little bit of a challenge. You can do the same thing and you can derive the sequence probability. And what you will see is that the sequence probability is also independent of the order in which you measure it. So the sequence probability also only depends on your histogram and not in which order it is sampled, which is quite surprising, I think, when it comes out. So here we have a process that is not exchangeable, but has sequence probabilities which, I mean, it is exchangeable, but it is not iid. That's what I wanted to say. And oops. So that would basically be one of the possible exercises that we could try in the afternoon. And that's an easy one. The interesting thing here now is if you look at the visiting distribution function and you ask yourself, how often does a ball hit a particular stair, then this is no longer a Gauss exponential distribution function. Now we have really a nice tip flow, and we have a tip flow with the exponent -1. So that's already a nice thing. So simply by breaking the symmetry in our process, that we have a let's say a relaxation time. So actually meaning that in the iid process I could jump around however I please. In that case, I really have a symmetry breaking towards for the system to prefer going downwards to the ground state, to the thermal ground state one. It's not the quantum ground state. Good. So one could do now exactly what we did before. We can compute that's the nice thing about this process. We can compute everything explicitly. So that's why it's a nice playground. Everything is fully under control. And in case one can derive now log of the multiplicity now was this product over the binomial factors. That's why you get here something that very much looks like I mean, comes from the binomial factors. That's why you get here this pi, and here you get the pi1 minus pi term. And the same you get for the cross entropy. You get the classical cross entropy term. So that's what you would get only for the iid case, but you get the additional term where you also have to respect the cumulative distribution function. And now even so that the exact tip flow you get if your stairs have all the same width. So if these qi's are 1 over w, basically. However, if your QIs are not 1 over W, but let's say that are themselves a power law, I to the power alpha, then the cumulative distribution function is something like an integral. So it's like I to the power alpha plus 1. So if my distribution function, and that's the exact solution for different for non-equispaced weights, so we get Pi is P1 times P1 now plays the role of a normalization constant, is then Qi divided by the cumulative of Qi. So if Qi is something like I to the power alpha, and the cumulative again is something like I to the power alpha plus 1, then the one divided by the other is again 1 over I. So you see that that Zipf law is actually something like, you could say, a tractor for the system. The thing, of course, breaks down if the power I to the power alpha for your Qi is smaller than -1, because then the integral is not just simply I to the power alpha plus 1 due to our integral boundaries. In the one case, if you start integrating at 0, this part drops out. But if your power is smaller than -1, then the power of the integral is still smaller than 0. Then if you have something like 1 over 0, so you get the infinity. So anyway, so there's a if your Qi shrink too quickly, then you get a different solution, because what happens then is that the ball always basically jumps to the next staircase, because if your next stair is basically larger than all the stairs below, which would be, for instance, also true for exponentially shrinking Qis, then the ball would basically just run down the staircase, and you get a flat Pi. Then Pi would be basically be equidistant. You get equidistributions. So these are the two different solutions, something that is close to equidistribution or Zipf law. Good. Then one can make the whole thing a little bit more interesting. One can say, okay, we introduce a driving rate, meaning that we do not always wait until our ball reaches the terminal ground state. We say at each state I, we throw a coin with probability lambda I. The next move again follows a SSR step, so you just sample some stair below. But with probability 1 minus lambda I, you just make an iid move. The only thing is that for if your ball reaches state 1, so lambda 1 always needs to be 0. So you always have to make an iid move, otherwise you are stuck in the ground state. Well, that being said, there's an entropy contribution coming from the coin, which is simply the entropy of a two-state system, and then the expectation value over all this coin entropy. Why this is important, I will demonstrate in a second. And that is, I don't know how much you still remember from thermodynamics or so. The thing is that if you look at thermodynamic relations, you have the second law. This second law says, okay, entropy can only increase basically in closed systems, and so you have ds is larger equal to 0. You have equal to 0 if you operate reversibly, and we will see tomorrow. Reversibly means quasi-static, almost static. So your velocities of your control is very, very slow. And then in that case, we know from thermodynamics that entropy or the other properties like internal energy and so forth act like a potential. So you can parameterize then, let's say, the internal energy with typically two numbers, the temperature and choose something. But in that case, let's say the easiest case, only with the temperature and the volume would be the second one. And however, if you operate irreversibly, then your system becomes path dependent. Then your internal energy is no longer a potential of your, let's say, pressure. What we usually have is we have this PV diagrams. So we have P and V, and if you have now a circular process in the PV space, then let's say the work integral, if you do it reversibly, is 0. So you go around a thermodynamic cycle, and you end up where you started before. So your let's say your internal energy just depends now on the volume and the pressure of your system, and that's it. If your system is irreversible, one more thing, it doesn't depend on how you go through this space. You will always have it. Now, if your system works irreversibly, this is no longer true. You will actually end up with some effective work that you lost. That is, you have had to invest irreversible work, and the amount of this work will depend on how you perform the cycle. So you lose this property of having a potential. However, as we will see tomorrow, this is a property of the mechanical interface. So irreversibility arises at mechanical interfaces. So as long as we do not consider a mechanical interface and just the thermal system per se, we don't actually need to consider irreversibility, and we can actually extend the potentials into a non-equilibrium process. So this is not an equilibrium process, but we get a Legendre draft that actually now still, like in the IIT case, like in the quasi-stationary equilibrium case, connects something that is now one could say a generalized free energy with internal energy, the temperature beta of the inverse temperature of the non-equilibrium system, which is well defined. And then we have to do something funny. We have to take the full SSI entropy, which is the entropy of the coin plus the path of that you take here, because you have the entropy of the distribution function that you visit, but you also have this entropy from the coin deciding whether mixing now SSR with iid moves, and what is relevant in this Legendre trafo is only the path part. So you have to subtract, but that comes out naturally, so you don't have to enforce that. It simply happens that on both sides of the equation, this driver entropy appears and drops out. And that this is actually really something that one should consider. I made now this plot here. So here we have the number of states that we consider. Then I did not, the driver ratio is 0.9, so lambda we chose 0.9 here, didn't write it down. And then what you can see is that the black line would now be the full SSR entropy, where we just derived the multiplicity of now these fast driven states, where a state now consists of two pair of observations. Which state did I sample? And at this state, does my coin toss say next move is a SSR move or next move is a iid move? Now, so this would be this black line. This would be this combined entropy. Then the red line is now the full entropy minus the coin entropy. So the red line is simply the entropy contribution that you get from the path. And the magenta line is that's the full line is the Shannon entropy of the observed distribution function. So we see that it's much larger than the SSR entropy in this case. That's the so-called conditional entropy that you have to apply in case if you have a Markov process. And we see, okay, the Markov process. So if we assume, if you measure the transition probabilities in the paths on the states, we would get that one. And we see that the actual entropy of paths is still lower. And that means that the path, if you throw away your knowledge about the coins, which coin was sampled, I want to point out this strange thing that if, for instance, you have here the staircase and the thing jumps downward, you actually, if you lose your information about the coin, you do not know anymore whether you had now sampled lambda I and you made the SSR move downwards, or you sampled 1 minus lambda I and you just sampled this by chance using the iid move. So this is the amount of information that you lose by throwing away the coin, and which means that the red line, so that the path, the entropies from the SSR path are actually what is called a hidden Markov process, and a hidden Markov process is no longer a Markov process. And how do we see that? We see that the entropy is actually lower than the prediction that we would get from the so-called conditional entropy. Now, two remarks to this. Ignore this line here below. This was an experiment. from experiments we do on trying to reconstruct entropies from data. And that's a lower bound we have there, so you can ignore it. However, you see here also this dashed line where the dashed green and the dashed blue line are almost on top of one another. And that's actually working very well, so you can use what is called the chain rule of transition probabilities. And with the chain rule, you can actually estimate the entropy of such trajectories very nicely, and also quite independent of the underlying process, as long as the correlations in the process are not weird, meaning as long as the correlations in the process are localized and not like you have, for instance, in spin echo phenomena that you get the spin echo after I don't know how many time steps, which so meaning that you, for instance, would have correlations that pop up again after 100, then after 1,000, and so forth time steps. So if you have weird correlations, then chain rule would have to be adapted. But if you just have localized correlations, which with a typical correlation length, then chain rule works pretty well for estimating the entropy. Yeah, actually, we're measuring what is called information production, but as we will see, information production and Boltzmann entropy are one and the same thing, or asymptotically, they're measuring the same. Good. That was that. We are in for an hour. Good.
Shall we have a break, or you feel like to finish the fourth one?
Do you? I see your eyes are sometimes a little bit dropping, so we can make 5 minutes break if you want to. That would be also maybe a good thing.
Yeah.
Then we reconvene in 5 minutes. It's a fantastic point because now we get to a slightly challenging topic. Not really challenging in terms of things. It's just longish, and then you need a little bit of concentration. So. Let's give them 2 more minutes.
Okay. Ja, ik denk dat, maar eerst was het één van de vliegtuig. Toen kwam ik uit de zon.
Okay, to continue, and so maybe let's briefly summarize what we had so far. So we said, okay, we take Boltzmann, the Boltzmann prescription, we can apply it to different process classes. If we have a consistent process class, which asymptotically can be understood as a multiplicity times a sequence probability, then the generic property divergence is cross entropy minus entropy always holds, and to some extent one can extend thermodynamic, the idea of thermodynamic potentials into non-iid process to non-iid process classes. Interpretation of these potentials is yet on the way, so we still have to understand what the free energy there means. And basically, this is something I really have to confess in here, is that entropy, if we go back and look at what von Neumann said to Shannon about entropy, that actually nobody knows what entropy is, and therefore he should call his functional entropy, because it gives him an advantage in discussions. I don't see that in that way, because actually I think through the Boltzmann entropy prescription, we know pretty well what entropy is, even though it's a construct, so we cannot directly measure it, but we can infer it. While free energy is much more elusive in that sense. So first of all, we see that if we generalize entropies, we also have to generalize our idea of free energy. And why free energy in some sense would encode work is we just can somehow understand in the most easy, so in the simplest iid cases, but yeah. So why this should be the extractable work if your system is non-iid, which is actually the systems we would like to employ for producing work, which are all non-iid processes, is, I think, more difficult than to understand entropy today. So the next thing is, we said, okay, we have now this Boltzmann side of entropy, which historically comes simply from the necessity that one saw at the time to find statistical explanations for thermodynamics. And then we have information theory, where actually the same entropy functional as the Gibbs functional pops up, and now we could say, okay, information theory to some extent is also just statistical physics, but not of gases in cylinders with pistons, but the machine is a different one. The machine that you look at in information theory is usually something like a cable, where you try to send information through. And so anything that could be called an information channel, that could be sound traveling in air, that could be text written on paper, it could be anything, depending on your information channel. And the idea is simply, so the questions of information theory are different. They ask two questions, basically, two very fundamental questions. And the one is connected with coding, meaning that if we have a set of symbols and I want to send these symbols, let's say we have the last 30 years of the New York Times, and we now want to send this information through an information channel. Then the question is, how do I code my alphabet into a binary code in such a way that it is minimal, so that I need the least bits to represent my data and send it through the cable. So that's the one question. The one question is, how can I efficiently code my data? The second question is arises and is more involved, is if you have noise and you want, and we will not talk about this, I just mention it for completeness sake here. If you have noise that degrades your signal, so some of your zeros and ones will be flipped on the way or lost on the way, then how do I have to code in order to repair these errors? Can I send the message in such a way that the receiver on the other end can reconstruct that here and there an error has occurred, and can correct this error. And there's actually a quite interesting phenomenon here that depending on the error rate, theoretically it's always possible to send a message, and now one has to be careful. Error-free almost certainly, which doesn't mean really error-free, but it means that the number of errors you make in an infinitely long message, you will only make a finite number of errors, so that the error rate goes to 0. While if your noise level is too high, in some sense, this is no longer possible. So there's some critical value where this goes on. And here now we have the chance to see that actually Boltzmann entropy and information measures actually the information production. So information production and entropy are more or less the same thing. And we will also see that at least for a large class of, again, a relatively large class of processes, this triangle retains an operational meaning, in the sense that we said before, Shannon-Gibbs entropy is actually less general than Boltzmann entropy, but with this, for the same reason, we could say it's exactly as general as Boltzmann entropy. Why? And that we will see in a second, because we can recode our data. And the point is now the following. I have some complex process, and I want to infer the information content or the entropy of this process X. X is now some random variable for some trajectories of observations. But what can I do now? I can apply a map, a reversible map, that maps my sequences, my X sequences, to other sequences Y. And if I can do that in a way that this adjoint, we call it the adjoint representation, is actually iid, then I can do the following thing. I can map my process to this iid process, measure the entropy there using Shannon entropy, and then pull it back to the original process. And this is possible for iid and the Markov case. So the adjoint representations could either be iid or Markov. In both cases, we can measure the entropy there either with Shannon entropy or what is called the conditional entropy. Now, there's a funny phenomenon here, which already reminds us a lot of what artificially intelligent systems do, or what neural networks do. They generalize. And in that sense, whenever you have a process that accepts a joint representation, then a process X implicitly defines a whole family of processes that work in some sense in the same way. Why? Because if I find a map I that takes my sequences X to these adjoint sequences Y, and the adjoint sequences are iid, let's take the simpler case, they are iid, then this process, the adjoint process, is uniquely characterized by its distribution function f. So I can or q, I called it q earlier. So that the probabilities to sample some symbol y in my adjoint representation. So what I can do now is I have here now a joint representation with a particular f, but I have now here this whole class of IID processes on the same alphabet, on the same symbol set, which I use to represent my joint representation, and I just would have to change my probability function there and get this domain of different processes there. And each of these processes I could translate back using pi minus 1. So in a way, I take this whole set here and can move it back to the original framework where we have a process X. And if you look now, for instance, you can Google that. There is a very funny example of autoencoders where they train the autoencoder using with images of kitchens. So you have a very complex process X, and they trained now this autoencoder with a lot of images from kitchens. And what you can do now is now you have each of these kitchens is in the autoencoder is represented by actually a long string of zeros and ones that is more or less you could, if you look at it, they look like random sequences, and in fact they are, because the autoencoder assigns random sequences to particular images of kitchens. And now you can do the following: you can take now two of these random sequences and make a convex combination of that. So you can actually slide along the line from a kitchen A to a kitchen B by interpolating these two random vectors. And the funny thing is, if you look at it at each point, you get the image. So the one kitchen somehow morphs into the other kitchen if you do that, while at each point you get the image that looks really like a kitchen. So you don't get this, almost never get these weird things that a door at some point may change into a fridge or a whatever, or a window, but all the time they look somehow the same. And something like that would also be possible here. So I could have a process X and I could have a process Y, and they would be represented on that side by a distribution function fx and a distribution function fy, fx prime, and then I can interpolate between those two and pull it back, and then I would get here something that is like a convex combination between, I can linearly interpolate between these two things. Which may remind us, there's just a side note, there's this whole business called information geometry. And information geometry is a slightly strange subject in the sense that they use something that they often call double flat metric, and which basically may capture these interpolation properties. But that is simply a speculation now. I have to check that. But it would fit. Anyway, so how can we do that now? So we have now here a sequence of random variables. So we have a path random variable if you want. So, and we have now particular realizations of these random variables. So this is a random variable with no particular value, but these are the values, these paths are the values that our random variable can sample. And now information production has a very clear definition, and already Shannon goes back to Shannon basically. And what you are saying is that that if you want to measure information production, then if you think you start with a sequence of zeros and ones, then you cannot represent your zeros and ones with other symbols that are shorter. So in order to be able to actually do effective coding, you usually do not look at the single symbols that are emitted by your process, but you are looking at chunks of symbols of length n. And then one subsequence type of subsequence can maybe appear very often, and another one appears very rarely. And then you can start to design information theory calls it prefix codes, codes in terms of zeros and ones that if you pass them together, you can still recognize them, because if you now make a sequence of zeros and ones, they should be designed in such a way that if you read the sequence of zeros and ones, you are actually able to segment it back into the meaningful words, which means reversible coding. You could code it in another way, but then you cannot segment it anymore because you have ambiguities that you cannot resolve. And in order to be able to resolve all the ambiguities, the information theory is just so-called prefix code, meaning that no code word starts with the same 0-1 sequence than any other code word. So they all have unique initial beginnings, and I would like to point out, I do not go into this, but here I want to note the so-called Kraft-Macmillan theorem, which basically tells us that Shannon entropy is the lower bound in coding efficiency. So it's that you can get asymptotically. And information production, basically, to get information production, what you're doing is you take your sequence and you cut it into always larger pieces, and then it is easy to show actually that for iid processes, the error you make with the optimal code at the length, with the patch length of t is actually of the order 1/t. So the error goes away is the longer you make your. And this is because Shannon entropy has this additivity property for independent systems. So if you have a distribution function of a system A and a distribution function of a system B, you make a joint observation, then the entropy of the joint system AB, S of AB, or H of AB is HA plus HB. And therefore, if you now, let's say, go from 1 to 2 symbols, you have now to divide here HA plus HB divided by 2. So you automatically do it right. And so even if you have local correlations in your system, this works. So here's basically what I mean. So if I have IID sequence, do IID observations, so all these xt are identical variables, then the upper, the ceiling function of the logarithm of 1 over p is t times, is larger than t times hp, because hp is the minimum, and this is what the Kraft-Macmillan theorem shows. And it's also smaller than THP plus 1. So if you look at the reduced entropy again, so you divide by T, then the maximum description length divided by T is the information production, and the information production is squeezed between HP and 1 plus P. So your error goes down the longer your patches become for coding. Exactly, this is what most coding strategies do, and now that's something we also can do. And now we could do something else. We could say, okay, we have now our sequence again, and now we say, okay, we can map to the adjoint representation. And so all what we are trying to do now is to segment our data stream into various segments. And then let's say this is A, B, C, A, C, B, A, and so forth. And that we call large A, and that we call large B. So we now give particular subsequences, we give them a new name. However, each of these patches has now an internal complexity A of original symbols. So while the classical information definition of information production always uses the same patch length T for cutting the data stream, one could also do it individually. One could use different words of different length. And then I have to replace this T if I now renormalize because what I want to have in the end is bits per emitted symbol in the original alphabet. So in the adjoint alphabet, I have to divide them by the average length of the words I use. And this is basically, and then I have to renormalize my information constant in that way, is actually the reason why complex processes are prone to exhibit tip flaw. Why? Because these patches now, if I now interpret these sequences into which I segment my data stream as words, then it's like I have a book, and the book is written in my Latin alphabet with 26 plus letters, and now I rewrite it in terms of words. So I'm now, my new alphabet is actually the lexicon of words I use for writing the text. And if I look at it that way, then we can remember something that is called random language, or the monkey typewriter model, where one can show that Zipf has actually looked at language, and Zipf's law is 1 over I, or 1 over n, tells you that if you look at the frequency at which some words happen in the text, and then you order the frequency along their rank, then these frequencies follow something that is very close to a 1 over x, to what is known as Zipf. The exponent may not be exactly 1, it's typically 1 point something or 0 point something, but around 1. And the reason is that actually Chomsky and Miller were the first one to analyze this in the 60s, was that on the one hand you have words decrease in probability with increasing length, and that's exponentially. So if you have a random language and each letter is sampled with a certain probability, and you have one space sign that segments now one word from the other, and that is sampled with a different probability, then we know that the longer a word becomes, the probability decays exponentially with the word length. However, also the number of possible words increases exponentially as they get longer. And if you now let the one effect fight it out with the other, or if you balance those two against each other, you see, and that's what Miller and Chomsky did. You see that the rank ordered frequency distribution is a tip flaw, and that is since we have now here something similar, if you now would do a maximum entropy principle on the adjoint side, where you now have to renormalize your information constant in that way, and you throw away all other constraints because you say, okay, I don't know them, then you automatically would get zip flaw. So you see that this recoding strategy somehow already includes the possibility that this is akin to language, and therefore you would also observe a Zipfian law. So with this, we leave the realm of exponentially distributed functions and go to the realm of power laws. Good. And now what we are doing is basically, if you were a theoretical physicist, you would say, all we do is this diagram is commuting. So what we do now is we have our original, that's what I said before already, but our original process X, we map it to the adjoint process. Here the adjoint process has a particular distribution function. This distribution function, we can, first of all, we can project it back to the original space. We can measure entropy here on this side simply using Shannon entropy because we have mapped it to an iid process. And particular to the process, we can define a lift operator that lifts us the distribution functions from the original process to the distribution function on the adjoint space. And now by identifying the entropy on that side with the entropy that we want to have here, then we are ready. So this is how we can define actually the entropy of a complex process that accepts adjoint representation. Not all processes need to accept such a representation, but those that do, this works. And the idea is basically, so that would be the intuition, how such a map might work. So we start with some random text example like here, and then we start to pass together we glue together some letters to find and extend our alphabet. So in the beginning, we just have our Latin alphabet, A, B to Z, and then let's say OM appears very frequently, and we say, let's take OM as an additional letter. And then we can go on and add additional letters until at the end here we end up actually with the text now not written basically in Latin letters, but actually in terms of words from the lexicon. So basically all we did is we made coarser and coarser segmentations of our original data. And this segmentation is this map pi that we saw on the original slide. Now, there are constraints, and these constraints come if I now measure my histogram on the adjoint space, then I know that my word, let's say extremely, the word extremely contains an E, an X, some E's, and some is a nice. Here we have already the examples. So the length of some would be 5, so it would contribute with L5 in the let's go back one slide. This 1 over expectation value of L. So we see now this constraint. So that the histogram on the original space and the histogram on the adjoint space have to match in that way. And so we can now really define our information production, because that's what we said is the case. So Boltzmann entropy is actually information production. We now measure entropy on the adjoint side, but in order to get bits per symbols in the original alphabet, we have to divide by this expectation value of the length of the words that we use. And then we get the same thing. So we get on the adjoint side, we get the information divergence, we get the cross entropy, and we get the entropy. And each of them with this particular renormalized units, constant for the units of information, so bits per symbol, and that's that. So now we have the entropy on the adjoint side, and now we have to pull it back to the original side. And this is, however, this is very general, because I can put in all the distribution functions on the adjoint side. I don't have to change my functionals to do so. However, if I want to pull them back to the original process, the entropy function, the divergence and the cross entropy for the particular representations on the original alphabet, they only can be done very particular for the process classes. So we cannot define them in any wider way. And okay, 10 minutes. So we can define this lift operator using the Kullback-Leibler divergence, basically. So if we lift now this distribution function, that one, we basically say, okay, we select this distribution function on the adjoint side, which has the minimum where the projection has the minimal Kullback-Leibler divergence with respect to the distribution function of phi. So this works all out. So again, we see we have now this maximum entropy, actually minimum divergence principle here, where we minimize now information divergence under a normalization constraint. So the F's are normalized. And here we have these matching constraints that match the distribution functions from the non-adjoint and from the adjoint side. And yes, these are now the projection and the lift operator. And yes, so that's how we can now define our entropy, cross entropy, and divergence in the original space simply by lifting the distribution function from the to the adjoint space and evaluating the respective properties there using the well-known classical information theoretic objects that we are used to. So even though this entropy is still log multiplicity in the original context, we can translate it into a situation where we can use Shannon entropy to evaluate it at the adjoint side. So in that sense, Boltzmann entropy and Shannon entropy still remain equally important, and we see we can make this whole diagram commute, and with that we can have a well-defined entropy functionals on the original space, as long as they accept this adjoint property. Now, the last 5 to 10 minutes in our session here today, Vormittag session, we now have defined, we have argued that we can get these entropy functionals by mapping to a joint space and pulling the results back to the original space from there. And the first thing we did today was simply to apply Boltzmann principle to log multiplicity, that we have such a thing. So implicitly it tells us that for every process that accepts such a joint representation, asymptotically this is possible. So asymptotically we will always see such a splitting of the probability into multiplicity and a sequence probability. And so all what remains is to show that the Boltzmann entropy that we defined in the first hour today, and the entropies, the pullback entropies that we got in the second hour now, are actually encoding the same thing. And we do this in an example. Yeah, we do this in an example of the SSR processes that we were looking at. The staircase process where we could compute everything explicitly. And why do we do that there? Because we can compute everything explicitly, and therefore we can actually also do the proof and full beauty. The proof for that the one actually corresponds to the other can be done generally. I won't bore you with that. There is, however, one thing that complicates things here in the proof is that we can actually show that the pullback entropies and the pullback cross entropy and the pullback information divergence are identical divergence, cross entropy and entropy that we get through the Boltzmann prescription, take the log of the probability, multiplicity, sequence probability, and scale it accordingly. However, in this proof, the only thing that we cannot show explicitly is that the multiplicity does not depend on the parameters of the system. So it could be, in principle, that our multiplicity is very particularly depending also on the parameters theta that we put there. So that's one thing. So for the Kullback-Leibler divergence, this does not really matter. But in the entropy definition, we always would like to have that the multiplicity only depends on the histogram and not on some other parameters, which comes actually from a thing that we did not discuss today. We will not discuss in detail. There's an alternative way to define entropy, and Shannon did this already. One is via information production. The other one is axiomatically. So Shannon basically came along with a few axioms which asked if I have a number of possibilities and I want to have a measure, and now I want to be able to address all these possibilities with a decision tree. And I want a measure such that accessing this particular sequence, the states is in with a particular is independent of the decision tree that I choose, then the only remaining possibility of this measure is Shannon entropy up to a constant, a multiplicative constant, which is the constant, the units of information themselves. And there are a few axioms, and the first one, relatively technical, just saying that it's entropy just depends on the distribution function, which is basically to say multiplicity only depends on the histogram. And that's why we would like to have it, because this is one of these axioms that Shannon used. There are a few more, and maybe we come back to it at another point. What is more important is that now we said that slowly driven SSR process is a Markov process. And since it's a Markov process, we can also use conditional entropy to measure the information production of this Markov process. And if we look at the chain rule again, we can, of transition probabilities, we can now, so that this would be simply information production, the definition, we expand Px 1 to t using the chain rule of transition probabilities. And I think I have to amend this a little bit. I lost a few brackets. And then we get the expression. This is basically the conditional entropy. And what we would like to show now is that the entropy that we got through the Boltzmann prescription equals the entropy that we get through the conditional entropy. And I don't do this now in detail because we first of all it will be only technical, just boring. It's just a lengthy computation. However, one can show explicitly that if you measure now the information production of the slowly driven Markov process, so the one where the ball always ends up in the ground state, or is only restarted once it comes into the browse state. We can show that the conditional entropy of the transitional probabilities really equals the SSR entropy that we derived earlier for the marginal distribution function at the maximizer. So that's important. So they don't agree away from the maximizer. They can give different results, but the maximizer they identify uniquely, and the numerical value of this one and this one are the same. So information we see now that Boltzmann, so this shows us that Boltzmann entropy is really a measure, is really measuring information production. And with that, what maybe a short summary. So it is possible using these coding strategies of recoding a data stream into some other data stream. Reversibly, we can, if the process accepts this, translate the process into an iid process, measure the entropy there, pull it back to the original space, to the original process space, and then what we also see now, this theta that we were talking about, this parameter set for the non-iid process, we now can identify actually with the distribution function of the adjoint process, so that this would uniquely characterize the process here. So theta would basically be the distribution function of the adjoint process, and so in that sense, Boltzmann entropy and Shannon entropy on the adjoint side are equivalent. And what one also has to point out is now that that we get process sensitive, context sensitive units of information, because our units of information had to be rescaled by this expectation value of the expected length of the words that we use for recoding. So that's that, and from that we also get this connection to Gibbs law. But context sensitivity is one thing that I think is enormously important for a lot of complex processes, and therefore this is also something that one should keep in mind, because we have grown up with iid processes as our mother milk. So we are so indoctrinated by our indoctrinated is not the right word. We are so conditioned from looking at iid processes, or from technology, mathematical technology that comes actually from iid processes, that it's sometimes hard to make this jump. Moreover, what is also changing is that our perspective switches basically from the idea of states, which is now something local, to what one would call an episode, or a path fragment. So we are not looking at state anymore, but we are looking at trajectories, or chunks of trajectories that we then pass together, and that would be a little bit like saying, if we look at the yearly cycle of a system, of a natural system, then maybe the June of this year is similar to the June next year, then this June would be to December, and therefore it makes sense to segment a year into, let's say, months or something. and therefore get a representation that is not localized now in, today we have 17 degrees and tomorrow we have 21 degrees, but we are looking actually at the sequences. And this time and again, I'm now busy with that for several years. And time and again, one has to really. So even today, I still make the same mistakes. Sometimes I think in terms of states where I should think in terms of trajectories. And this is something one has to train. It's nothing that comes overnight. And it's maybe one of the most important things when you go to complex processes is that the idea of state becomes somewhat weakly defined, and it's better to think in terms of sequences, paths and sequences. And with that, I think I stop, and then we can now enjoy our lunch and